Well, good afternoon, everybody, and welcome to Astronomy Days. We're so glad that you could be with us for another year of exciting astronomy, astrophysics, space stuff. That's right, the North Carolina Museum of Natural Sciences is bringing you another week-long, whole space convention right here from downtown Raleigh. So it's great to be with you all. I'll be your host for the first presentation of Astronomy Days. I'm so excited I get to help kick off this event. My name is Chris. You can call me your space host, coast to coast. But hey, as always, it's great to be with you for virtual Astronomy Days. Now, we have programs today through next Sunday. So make sure that you're checking out naturalsciences.org/astrodays to get the latest on all the programs that we've got coming up all week long. Sign up for all your favorites. We'll send you reminder emails as well. And we'll have a great time learning about space and all that there is to it. So to get started, we have folks who are joining us in the Zoom call and who are watching on YouTube. Hello and welcome to all of you. Make sure that you are hanging out in the chat for today's program because I want to get your thoughts and your questions about today's topic as we go through the programs. So we do have our moderators who are standing by to help answer any questions that may come up, or if you need assistance using Zoom or YouTube, they're there. Everybody drop a waving emoji to our moderators to say hello. If you're watching on Zoom, I am going to go through a quick tutorial just to make sure we're all on the same page and show you how to use some of the tools that are available to you today. So first off, everybody should be muted, but there's a button in the bottom left-hand corner to make sure that your audio is turned off and make sure that your video is turned off as well. We are recording this program, and I don't want anybody's faces or sneaky audio getting into the show. More importantly, down there in the bottom of the screen, there is a closed captions button. You can see it marked here. Make sure that if you would like to have the captions turned on, you click on that button and then click where it says Show Subtitles. That'll give you access to our live caption feed. You'll be able to adjust the settings if you need to, like the size of the text to help you read it if necessary. And then to give you an even better viewing experience, we recommend that as we go through today's program, up in the top right of your Zoom screen, change the view that you've got to speaker view. That way you can see the content and our guest as we go through the program. Side-by-side mode, we think, is one of the easiest ways to view the program. That'll give you the best experience so that you can see everything that's going on. And between the two screens, there's a little slider if you want to adjust between the sizes of the shared screen and the camera view. And like I said, make sure that you're in the chat, say hello. And as you have questions, go ahead and pop them into the chat, right? Question pops up here, drop it into the chat. That way our moderators have those queued up for me. And after the presentation, we'll be able to ask your questions to today's guest speaker. Of course, the chat is open, so we also expect you to be nice. Be nice to the other people on today's program, be nice to our guest speaker, and most importantly, be nice to me. That was a joke. But I didn't see our guest speaker laugh at it, so we'll, okay, thanks. And with that, that's a great opportunity for me to introduce our very first guest speaker for Astronomy Days. And we couldn't have got a better guest speaker to kick off Astronomy Days with the North Carolina Museum of Natural Sciences than our own head of the Astronomy and Astrophysics Research Lab and a professor at Appalachian State University, Dr. Rachel Smith. Hey, Rachel.
Hey, Chris, how are you?
I'm doing great. It's Astronomy Days. It's a great time.
Welcome, everybody. I'm so glad everyone showed up on Monday.
Yeah, here we all are Monday, right after 12 o'clock. And we've got a huge crowd of people between the Zoom and our YouTube viewers.
Awesome.
I think are excited to learn a little bit about what it means to travel through OpenSpace.
Sure. Just let me know when you're ready. Should I start sharing?
I think we should jump into it. Yeah.
All right.
Let's blast off. Let's get to space.
Okay, well, welcome everybody. So the title of my talk is Planets in the Habitable Zone, a journey to the past, present, and future of life in space, which is a lot to talk about. And I'm really going to concentrate on the habitable zone in our solar system. And I'm going to jump right in here. And I'm going to hide, hold on a second, hide the floating things. Okay, so how does this look, Chris? Are we good?
That looks great to me.
All right, so what I'm showing you, just to let you know, is I'm using software called OpenSpace. I think they're going to put the link in the chat, but I'll just tell you it's openspaceproject.com. It's free software. We're part of a team led by the American Museum of Natural History in New York. This is a NASA-funded project now in its seventh year. Well, time flies. To create really cool programs and with this Fly Through the Universe software. So everything I show you is based on all real data. So the star fields you see are in their correct place. The data sets are all from NASA mission data sets, and the terrains I show you on Earth and Mars and other places we'll go are all from mission data. So keep that in mind. And what's really cool is you can fly from Earth to the end of the universe. And today we're kind of going to stick to our galaxy, maybe go a tiny bit beyond for a second, but really we're going to stick to our galaxy because we're talking about habitability. What does it take to have a planet that can support life? And so first of all, what I'll start with is our solar system. And I'm sure you all know that, by the way, Chris, interrupt me if the visuals look weird, like with bars, because something just popped up for me. So tell me if that looks weird on my screen, on what you're seeing. Are we good? Okay. Okay, so this is our solar system. And so we have 8 planets. And there is a zone, which we're going to talk about, where life can exist in our solar system. And that is called the habitable zone. And I'll show a picture here. That is a disk. This is a protoplanetary disk, a sketch of a disk. And this is how all planets, we think, form from a disk of spinning gas and dust around one or more stars. Our solar system, of course, has 1 star, but many have more. And this is what's been really exciting in this kind of age of exoplanets, of learning about planets beyond our solar system, is that there are so many interesting different types of systems in our solar system. And so we might be unusual in how we form, but the physics is the same. And so from this disk of gas and dust, it takes about 1 million or so years for them to, for all the gas and dust to form, to kind of mush together to form planets, or the material falls onto the star, or it blows off into space. And the leftovers from that disk are the asteroids and the comets. And what I'm showing you here in the center here, between Mars and Jupiter, are a couple of the data sets that we have in OpenSpace, just showing these remnants of asteroids. And when they hit Earth, they're meteorites, and we can learn about the early solar system from these remnants. This green orbit here, I'm showing you orbital trails now. This green orbit and this red orbit, these are Kuiper Belt object. This is a famous Kuiper Belt object, which you all know as Pluto, but it is now not a planet. And you can kind of see one of the reasons why is that when we flip our solar system to see the disk and the plane of these orbits of the planets, we see how Pluto is really eccentric. It goes way up above the orbital plane and down again. And it's one of thousands of bodies in the outer solar system out past Neptune that have this type of orbit. And it's one of the reasons Pluto is actually not a planet. But it's still really interesting, and objects where Pluto lives come to the inner solar system and are our comets. But today we're talking about habitability, and what I'm going to do in OpenSpace, you'll see me periodically turn data sets on and off. And by the way, I'll mention this is free software. You can download it, and if you have a decent machine, you can play around with it. Hopefully, it works best on a PC, I'll just say, versus a Mac. And so we're talking about habitability. So what does that mean? And we're going to come back to this again when we talk about Venus and Mars and exoplanets. But there is a zone around every star that's called the habitable zone. And here it's shown in this gray band right here, where Earth is nicely set in the middle. So we have life on this planet, we have oceans on this planet, and it's defined by NASA and other astrobiology and scientists as the zone around a star that can have, where a planet could have liquid water on the surface. And the reason it's defined that way is that we know, as far as we know, all life needs liquid water. And there certainly could possibly be life beyond the habitable zone, such as Mars under the rocks, or maybe around on a moon we'll talk about, of Jupiter. There could be life beyond the habitable zone. But when we're talking about thinking about intelligent life, meaning, as we define it, life that can create a telescope and interstellar travel, like we have done, we really have to consider where there's liquid water on the surface and a terrestrial or rocky planet. And so we'll talk about this habitable zone. And then today we'll also discuss what happened to Venus. Venus is our, you might see our evil twin or our searing hothouse, or you may have read it is sometimes called hell, a hellscape, however you want to call it, because it's really hot and it's in this way inside where the habitable zone is. It's too hot. And out here, it's too cold. And that's where Mars and everything beyond that, beyond Mars is. And it's too cold to have life around on Mars. But this wasn't always the case. And we can learn a lot about what happened in the early solar system, how planets formed, and what's going on, what happened to Venus, what happened to Mars, because we want to understand the future, not only the future of our planet, but the future of humanity, maybe going to other planets, and what will it take for us to inhabit another planet. So all these planets, even though they're not habitable right now, are still tell us a lot of really interesting information. And it's possible that there are exoplanet systems with several planets in the habitable zone. And you can imagine what that might be like. You could have neighbors on another planet. So we're going to go to our first stop is Venus. And we're going to talk about Venus first. And Venus, Venus is a really interesting planet. It's not habitable now. It is quite hot. It's about 900 degrees Fahrenheit on the surface of Venus. It is hot enough to melt lead on Venus. And what you'll see in OpenSpace is a surface, because if you didn't take out the atmosphere, what you'd see is this. Venus has a really thick atmosphere of sulfuric acid clouds. It's filled with carbon dioxide, a greenhouse gas. And basically what happened with Venus, we think, is that it's possible about 1 billion years ago, it was a blue planet like Earth, and it had oceans, and it could have been habitable, but Venus is close to the sun and was subjected to what's called a runaway greenhouse. And what that means, I have one diagram of this, is that if you can imagine, if you take Earth and move it to where Venus is, you get this feedback loop of greenhouse gases going up into the atmosphere and no way to get them out of the atmosphere. Venus doesn't have a way to move molecules into the rocks like we have plate tectonics. We know about them from earthquakes and volcanoes. And the plate tectonics, the movable crust on Earth, keeps our planet habitable because it takes out all of that CO2 and puts it in the rocks as carbonate rocks. And so Venus doesn't have that. And eventually it got too hot. All the oceans boiled off, and there was volcanism on Venus. So all the sulfuric acid got into the clouds, and it's now a searing hothouse, completely not habitable. But we can learn about Venus, and Venus will tell us if we don't get our greenhouse gases under control on Earth, we could possibly be subjected to the same fate. Not because we're closer to the sun, but because we're just pumping out greenhouse gases without really controlling it. And so we need to learn about what that would mean on Venus. Okay, so let's go to the surface. Venus is really interesting. And there are actually some missions that made it to the surface of Venus, which is really cool. And what you'll see here, there are volcanic craters on Venus and impact craters from asteroids that hit Venus, just like they hit Earth and other planets and moons. And all of these really interesting grooves. They're called tesserae, which I think they're going to put in the chat. It has to do with caked lava and these ancient lava flows we think happened on Venus. And you can explore this planet with OpenSpace and zoom down and see some of this terrain. The data from this that you're seeing here are from the Magellan mission, which is a mission several decades ago by NASA, which mapped the surface with radar imagery. And you can kind of go down. It's really very alien looking, not like any other planet we have in our solar system. It's got these really light colored ancient lava flows. Here's an impact crater. And there is absolutely no life on the surface that we know of, and no life as we know it could really survive on Venus, we don't think. Interestingly, if you tried to go to the surface of Venus, you would not survive. It is like being under 3,000 feet of water. It is extremely high pressure, 900 times or 90 times the pressure of Earth, I should say. But the Russian mission Venera, when it was the USSR, went in the 1960s through 1984 and took the very first images of a planetary surface on Venus. The mission lasted 2 hours on the surface. It got to the surface, took these actual images, and then the spacecraft just melted. And they knew that would happen, but they were successful in getting these very first images. This is one of the first, this is actually the first, as far as I know, from 1975. The very first images on the surface. And what you see is a cracked, dry, very hot surface. But to me, this is one of the most fascinating missions, being able to get through that atmosphere and see the surface of this searingly hot, uninhabitable planet. Here's another one. You can see it tells you the pressure, 90 times the sea level of Earth, and this is about 900 degrees Fahrenheit. There are some new missions coming, and what was exciting about last year, 2021, 2 new missions since were approved by NASA. The first is Veritas, and that is a mission that's going to map the surface. This is a schematic showing mapping the surface in very high resolution to really see in greater detail with better technology than in the 1970s, 80s, and 90s, what's on the surface of Venus. Could there be active volcanism still? What can we say more about the planetary geology? And then, to me, even more exciting, although a complementary mission, is Da Vinci. This is going to be an atmospheric probe. It's going to go down into the atmosphere and look at what's happening in the atmosphere of Venus. And this is critical to understand this runaway greenhouse, to understand maybe there's little, there are possibly ranges of life where life could exist on Venus, although there's no proof at all that there's any sign of life. There was a recent detection of a molecule called phosphine, but that has now been a little bit a shaky observation, not even sure it's phosphine, and not even sure, and it's certainly not been proven that it's due to life. But these missions, which should launch in the late 2020s, will tell us so much more about the surface of Venus, which is really exciting. Okay, so I think that's all. Yep, that's all I have for Venus. So this is Venus, our sister planet, was in the habitable zone, and now it's way too hot. And sometimes you may have heard that there's a term called the Goldilocks zone, and that is a term used for talking about being just right. And that's where Earth is. So let's go to Earth, and we're going to make a stop at Earth before going on to Mars. And where we're going to stop is, if I can find my, here we go. We're going to set a bookmark, and we're going to go straight to a place where this is Earth. And by the way, I'll just take a quick stop. What you're seeing here in OpenSpace is the Earth, the orbital trail. This is a line that goes to what's called L2, which is it stands for Lagrangian point, and it's one of the 5 stable orbits, the 5 stability points around where the Earth orbits the sun. And this is, as you may have heard lots in the news in the last few weeks, is JWST. This is the orbit of JWST, which is basically doing a halo maneuver around the Lagrangian 2, about 1 million miles from Earth. This is the moon around Earth, and we'll take all these great images, also take a lot of, not just images, but data on exoplanets as well. And we'll just think about JWST when we talk more about exoplanets. The moon, by the way, we have a huge moon. We have a very large moon, and we think that that moon is critical for keeping our planet habitable. We have a blue planet. You've heard about the blue planet. That's us. We're covered 75% with ocean. That's amazing. But it actually, by mass, is not very wet. It's about 0.6% mass of water. And there is so much water in the universe, let alone the galaxy, that we think water is plentiful out there. And basically, this is one of the reasons we search for life, is that there is so much water out there. I'm just making it daylight in California now. Oops. There we go. All right. So why are we going here? Well, we're making 3 stops on Earth, because we have a lot to cover today. 3 stops on Earth, and I made a little bubble with OpenSpace so I can find it, because they're tiny little spots. These are the San Francisco salt ponds. And the reason we're making these stops on Earth is that scientists have found that there is life that can live in very extreme environments on Earth, not these comfortable environments we live in on the surface, but or as we define as comfortable, but these are microorganisms that live in very harsh conditions that we think could have an analog locations in space. So because the microbes live here, these sometimes called extremophiles, because they live here, we think that this really inspires us to search more in space. And so what you see here, these are really beautiful, actually. This is all real data from satellite imagery. These rectangles and other formations, these are the San Francisco salt ponds, which are right outside the San Francisco airport. And you can see them from the plane if you ever fly in or out, hopefully both directions if you don't live there. But anyway, they're colored because of the enzymes that are these microbes live inside the salt. So they're called halophiles. They love salt. Halo is salt, phile is love. They love salt. And we think, astrobiologists study microbes like this to say, okay, these microbes can live in these really, really salty conditions that, with high concentrations of salt. Therefore, it's possible there are organisms that could survive in the oceans of Europa or in the briny ocean of Mars, not ocean of Mars, but in the water that could live that could exist under the rocks of Mars. And so these organisms like this have really moved astrobiology along in terms of what kind of life could we find beyond the habitable zone in our own solar system. So this is one place that I really like to show because it's very, you can see it, and it is one of the great examples of extremophiles on Earth. Another example very close by is in Grand Prismatic Spring, which is in Yellowstone National Park. And again, it's one of these very well-known, if you've ever been there, places that has these beautiful colors, again, because of these microbes. And we'll just get down there. Where is it? It's super tiny. I have to let it load in. These data sets can be rather large. There it is. So I am going to quickly, again, takes a little bit of practice to get all of this working. Remember, when you use OpenSpace, to think about it's still in development. So it's fun to use. It's not been fully packaged yet. Oops, I'm trying to make it more bright. Here we go. All right. So this is Grand Prismatic Spring. It is in Yellowstone National Park. It is, again, has these gorgeous colors like a rainbow. And that's because the microorganisms that live here are called the thermophiles. Thermo is heat, phile is love. They love heat. Really hot, 200 to 300 degrees Fahrenheit in these boiling springs. You can actually see the footpath here going from, and there's a couple of springs here, but this is Grand Prismatic Spring. And there's a footpath, and visitors to the park can actually visit the pool. It's really, really hot. And these are one of the, as a group, one of the first extremophiles discovered a few decades ago. And again, really brought into light the kinds of organisms that might be able to survive the extreme conditions of space. So where could thermophiles live? Maybe under the ocean, under this global ocean of Europa, where Jupiter is keeping it really, really hot. So we have organisms, we know of organisms that live in the deep sea vents that also can survive extreme heat and live off methane and no sunlight. And we have organisms in Grand Prismatic Spring, which are similar, which can survive this extreme heat. So this is another location that has also inspired the search for life beyond Earth. And the last place we're going to talk about is in Turkey. And the reason we're going is it has an analog environment on Mars, and that is going to be our next stop. So let's go. Here I made my little bubble. This is the orbit, you may have guessed, of the International Space Station. And of course, we have astronauts up there studying all really interesting things about microgravity and doing all sorts of experiments. And one day, hopefully, we can get more than a few 100,000 miles beyond our planet. We've got a really long way to go to get to the stars. And hopefully I'll put some of that in perspective today. Okay, so the last spot is Lake Salda. This is in Turkey. And this is a really interesting lake. This little lake, which is used as a recreational area. and I'll leave my little bubble on, but here it is. This lake has a shoreline, this bright white shoreline here. And this shoreline is made from microbes. It's called microbiolites, and this shoreline has been studied a lot in terms of what could have created the minerals around this shore. And ancient microbes and current microbes can do that. And the reason that I'm showing you this, not only to understand life on Earth and how microorganisms could evolve, and the earliest life on Earth created similar types of mineralogy here, is that the satellite over a crater in Mars, over Jezero crater specifically, has seen similar chemistry as this shoreline. And so you may remember, if you were watching Mars 2020, the landing in 2020 or early 2021, landed on Mars, landed on Mars and in Jezero crater to study this ancient shoreline that has this, that this is an analog for, or that's an analog for this, however you want to think about it. This is an ancient delta that is feeding into this lake, and there's a very similar formation on Mars that is one of the many, many examples of water that flowed on Mars in the past. And so we think about this lake filled with water that enables life. One of the many examples we have on Earth, of course, that life can survive. We have lots of water on our surface, and it's possible, it's really likely that 2 billion years ago, Mars was also a blue planet. So let's go to Mars and think about that. We'll go right, I'll mark Jezero, and we'll fly to Mars. One nice thing about OpenSpace is you don't have to worry about speed of light constrictions. You can just fly around very quickly. We are limited by the speed of light, and that has kept us from going far at all. So this is Mars. Mars probably had, definitely had water in the past on its surface. There's many lines of evidence for this. It has ancient river channels, the delta, the many craters that show evidence for water, and it could have had an ocean in the northern hemisphere. And so I'm going to go right to Jezero. So Jezero is where Perseverance, that rover, landed a couple years ago. And let me turn Mars back on so I can get, all right, and make a day. And we'll just go, this is our one stop on Mars because we don't have time to go everywhere. And I want to show you, we have to talk about beyond our solar system too. Okay, so and what you see here, I'll just mention in terms of data, which I think is kind of interesting, is these little dots that you see are high resolution data sets from the Mars Reconnaissance Orbiter, which is still orbiting Mars, taking lots of data so we can understand the surface. So not only do we have rovers on Mars on the surface, we also have a satellite that goes around. And with OpenSpace and lots of other types of visualization scientists use, we have part of the, we don't have everything loaded in to show all of the data at one time as high resolution, but we do have some data sets. So you'll see that as striations here. And I'm just gonna zoom in here. So, it takes a second to load. We're talking about really high resolution data sets, but here is Jezero. See it right here. And oh, good, I'm on Mars. Good. So Jezero crater. What you see here is this beautiful, beautiful crater. It's going to take a second to load in all the data. And there are all of these channels feeding into the crater coming in from this direction. As soon as that loads in, you'll see it. So this channel coming in is like the Mississippi Delta, or like the smaller delta you saw at Lake Salda on Earth. This is an ancient river flow. We see lots of impact craters on Mars, and this ancient river flow is really important. We want to send rovers. We want to do science where there could have been water, because where there could have been water, there could have been life. And we might find fossil life on Mars. And that would be, we're really trying to know, are we alone, not only in the solar system, but of course in anywhere. And we don't, even though it seems probable that there should be life out there, we have no evidence for it. And so scientists are really trying to study this and figure that out. So this, so basically Perseverance landed right about here. I have a picture of it. This is Perseverance, and here's that shoreline I'm showing you on the other side in OpenSpace. And it landed, so that's that shoreline here, and it's driving around looking at samples. It is caching samples, which means it is storing samples on Mars for future pickup from a return mission. And that is really important. We want to bring samples of Mars back to Earth. Right now, the only sample from Mars we have on Earth is from Martian meteorites. And those are bits of Mars that got blasted off. We don't have a lot of it. And we really want that pristine soil on Mars. So Jezero is one of the many, many examples, water flowing on Mars. There was once life. But what happened? Oh, well, first of all, I'll just say for this mission, Mars 2020, what I think is one of the coolest things is that it has we now can fly a little helicopter on Mars. It is Ingenuity helicopter is the first powered flight on another planet. And some of you may recall that in 1903, the Wright brothers, Kitty Hawk, North Carolina, so we're here in North Carolina, first airplane. And now in 2022, we have the first powered flight, not too long actually, and on a cosmic scale, it's like nothing, no time at all. We now have a little helicopter that can be flown remotely. There's an actual image of it taken by the rover, and this is called Ingenuity, and it's done many powered flights. It goes 10 to 30 feet up in the air, and it's surveying regions where Perseverance might go. And even beyond just the science, the engineering of it was a real marvel. They weren't even sure they could fly on Mars because it has such a low atmospheric pressure. It's like 0.6% of what it is on Earth. It's not the same kind of engineering to fly an airplane. You have to engineer something that can be able to fly in a thin atmosphere. This is the image of the actual drone taken by a close-up, taken by Perseverance. And here is a faraway view of it just flying right up there from the surface. So Ingenuity is a really fascinating little helicopter, and future missions will benefit from this technology. So what happened on Mars? Why is it not in the habitable zone? And the main reason, oh, well, here I'll just show you, sorry, I forgot I had this, is these are stromatolites. These are the types of organisms, these columns, these black blobby things. These are made by microbes, very similar to the ones that make the microbialites that I showed you on Lake Salda. And it's possible, this is from Australia, that a similar terrain existed on Mars with ancient microorganisms, that we see this chemical evidence, not of microbes exactly, but of this mineral that they produce. And so they can produce. So we have to prove, we don't have evidence yet that there's biology on Mars, but certainly there's really cool places to look because of the minerals there. Okay, so what happened on Mars? Basically what I'm showing you here is you have Mars on the left here and Earth on the right. Let's look at Earth for a second. Earth, these lines are Earth's magnetic field. So Earth has this magnetic field that you could think of like a force field that's keeping us protected from the solar wind. And these are the high energy particles from the sun that are stripping off our atmosphere. And we have this protection. We have this magnetic field is key to our habitability, and we think is key to any planet's habitability, because you have to be protected by from your host star. We need that star for heat and light and energy and life, but we also have to be protected from the storms that can be caused by these stars. And especially for habitable zones that are closer to their stars, which I'll show you some examples of in a second, they need to have these magnetic fields, we think. Mars does not have that. Mars lost its magnetic field around 3.5 billion years ago. That's when Earth was kicking in with life. So possibly there was a time, a short period of time, when both planets could have been starting life. But Mars lost its magnetic field, and and because of that, the solar wind has stripped away most of its atmosphere, and the oceans evaporated. And now it's not a habitable planet anymore. It's not in the habitable zone any longer. And the MAVEN mission this is a schematic. This is MAVEN, this little orbiter that's going around, it's still around Mars. It was studying this upper atmosphere and really proved that it is the solar wind that's affecting Mars's atmosphere still. So you have to think about what do we do if we want to send astronauts to Mars, if we want to really make this our habitable twin planet, what does it take? And it would really take figuring out how to protect Mars from the solar wind. And there's been ideas out there, lots of ideas that we have no technology to really do yet. like putting up a magnetic shield or somehow creating an artificial atmosphere with pumping out greenhouse gases and figuring out a way for Mars to hold on to those gases. But big thinkers like Elon Musk, this is a schematic from his engineers thinking, what could a human habitat look like on Mars? We know Elon Musk and SpaceX are heavily involved in collaborating with NASA to get astronauts, American astronauts especially, back to space, and eventually really be part of this international collaboration to send astronauts beyond the moon. Right now, the moon is the only other body we've been to physically, and eventually Mars, but it's not easy to do that. There's a lot of issues that come into that to work out. But maybe one day there'll be a habitat, and then maybe after that, we can terraform this planet somehow, and this could be us one day as Martians living on Mars. Who knows if that'll ever happen? It is a long way off, if at all possible. Okay, so that is where we're going to go with Mars. And before we leave the solar system, I'm going to take us to one other place in our solar system, which I know you've heard of, most of you probably, but if not, we'll talk about it. This is a moon of Jupiter called Europa. And we'll see Jupiter. Here's Jupiter. Here, I'll turn the solar system around so we can have our nice little, you can see the remnants of our protoplanetary disk, by the way, by the orbits of these planets. I hadn't mentioned that. Here's Jupiter, the biggest planet by a lot in our solar system, protects us from asteroid impacts. So thank you, Jupiter, for that. And here's Europa. And Europa is a new mission was approved called Europa Clipper that is going to study the atmosphere of Europa even further and take more measurements of the surface. But we think pretty sure that Europa has a global ocean. It is a moon that's smaller than our moon, but probably has more water than the entire Earth. That is a really important place for astrobiologists to look. Still beyond the habitable zone, because it's too cold for water to exist on the surface. However, there could be microbes, there could be something under the surface, and we need to be able to, we really, really want to go explore. These cracks are from the water, this really salty, briny water coming up through the ice, and it cracks periodically. There are some impact craters, and this is a really important moon for astrobiology. The Europa Clipper will launch again in this decade with all these other missions going out to study Europa in greater detail and maybe one day get beneath the surface. Okay, so as before, we're going to end beyond the solar system, but before we do that, since we're in the outer planets, I'm going to quickly mention that there's a mission called Voyager. And Voyager is really cool for lots of reasons. This mission, these two probes, launched in the 1970s and late 1970s, and they went out to study the outer planets, took some images of Europa, images of Jupiter and Neptune and Uranus, etc., and really was sent out to study these outer planets and their moons. Right now, Voyager is the farthest we've ever sent anything. It's past the orbit of Neptune. It's past what sometimes you may hear it's in interstellar space, but it's still going out to this outer cloud of comets way at the very edge of the solar system. We think it's called the Oort cloud, O-O-R-T, and it will take thousands of years to get there. And one of the probes, at least, is headed to Proxima Centauri, which we'll look at, and we'll look at the system in a second. But it will still take 20,000 years to get there. So space is very big. It is mostly space. This is the fastest mission we've ever sent. It goes 1 million miles per day, roughly, and it still will take thousands of years to get to the end of the solar system, and then more thousands of years to get to our closest neighbor, Alpha Centauri. So, and Proxima Centauri, they're around the same area. But even given these distances and understanding the very remote probability we'd ever find life, Carl Sagan was really heavily involved in this mission. And he thought, even though we'd be long gone if this ever happened as a race, as human race, and the planet could even be gone because, you know, the sun is only going to live another 5 billion years, he decided we need to show, first of all, we need to look back at our planet. And he showed the Earth before he thought about SETI, extraterrestrial intelligence. He wanted to look back at Earth. And this is the very first picture ever taken of the Earth as a dot. And this is a sunbeam. And he wrote, based on this picture, the essay Pale Blue Dot, which some of you may have heard of. And it basically is about thinking about our planet in a different way. And it really did put in perspective how small we are and how yet, even though we're a tiny pixel, everything that's ever happened on this planet, everything, the entire history of humanity, the entire history of all the life on this planet took place on this little dot. And he was also very much against war and conflicts, and really thought that this type of image would help people put in perspective how to take care of each other and this planet and everything. And one might argue we're not doing so well in that, but this was the very first time we saw the Earth like this. So he thought looking back at Earth is really important. We need to put ourselves in perspective. As we explore space, we have to keep ourselves in perspective. And he put on these golden records, and these are, each probe has a record, which are images and sounds of Earth. And he thought in the very smallest chance that any extraterrestrial would find this probe, we would never know about it. We'd probably be long gone, that at least they would know we existed. And the golden record is one of the few relics we have of our solar system, of our existence on Earth out there. So, so before I talk about this, what I'm going to do quickly, I'm doing okay on time, yes?
You're doing great.
All right, awesome. So what I'm going to do, actually, before I turn on the exoplanets, well, you know what? I'll turn them both on at the same time. All right, so we are in the solar system, and I'm going to do two things. I'm going to turn on I turn on the exoplanets, I can't spell, and I turn on the radiosphere. So two things are on. So we have two data sets that we're looking at. Two data sets of exoplanets and a sphere that represents our radiosphere. And what that is the farthest we've sent signals out from Earth. So we've sent radio signals because the invention of the radio was roughly 100 years ago. And here you see the solar system flying away. We've sent signals out from Earth for about 100 years. And so that means that any extraterrestrial who would find these signals could only be within 100 light years at this point, because it takes light, light, there's still a speed of light problem. We can't go at infinite speed. The fastest anything can go is the speed of light. And of course, rockets are much, much slower than that, fractions of a percent of that. So if Earth is in the center, this is as far as we've sent signals. And as I zoom out, you'll see some of these exoplanets. These are our closest neighbors. This is our neighborhood. If you live in a neighborhood, these are your neighbors. On a cosmic, remember, our closest neighbor is Proxima Centauri, 4 light years away, well within this sphere here. But as we zoom out, all I'm going to do is I'm going to zoom out to the galaxy to give you a perspective of how far that is. Again, this is us, a little blue dot, and in fact, we're within that dot. And here's our galaxy. So this is our place in the galaxy. So we haven't sent signals anywhere close to the entire galaxy. We haven't even explored with telescopes. We have with some technology explored, but in any detail, really know all of the exoplanets out there and what's out there. And if I just zoom out a tiny bit further, you'll see these other dots. So we are one of hundreds of probably 400 billion galaxies, and there are about 400 billion stars or so in each galaxy. So there should be life out there, probably. But again, why don't we have evidence for it? We're limited by technology, but we're also limited by the speed of light and the limits of interstellar travel, possibly. And certainly for us, we haven't gone very far. So the exoplanets, when we think about habitable zones and we think about going to these exoplanets, one thing to keep in mind is we don't know what's habitable yet. And that means if we look at an exoplanet, we try to study its atmosphere, we have to know, how do we know there's life there? And we don't have that answer, but there are some molecules. I pulled this from a recent publication, just showing, all I intend to show here is these are some of these molecules and the spectra of these molecules. So the fingerprints of each molecule, you have methane and other oxygen, and all these other molecules that could be indicative of life on a planet, but we don't know what combinations really constitute life. And we can't say for sure that this combination means there's life. One thought is that it has to be out of equilibrium in order, because we've really thrown our atmosphere out of whack from a regular chemical standpoint. We've got lots of greenhouse gases. Maybe that's an indication of life, but we don't have this answer. And hopefully JWST will answer some of these questions in really getting better images and better spectroscopy of exoplanets. So let's quickly, but I was going to end with some of these exoplanets. And the first one I'm going to go to is our, I first have to turn off. It doesn't like it when I have the exoplanet data sets on. And I'm going to turn off the radiosphere real quick if I can find that. Okay. So let's zoom to Proxima Centauri. So what we're going to see with OpenSpace, what's really nice with the new version is you have the habitable zones all worked out for all of these systems. And there's so many exoplanet systems that have been discovered. Well, you won't see in OpenSpace, I'll just say, which is, could maybe be in future versions, is you don't see multiple star systems. So there's one star represented for each system, but you can read more. There's an exoplanet website that I gave the program committee to send out, which is really good. It's from NASA talking about these planets. Okay, so here's Proxima Centauri. This is 4.2 light years from us, like your next door neighbor. Still, just to keep this in perspective, if you were riding on Voyager, you could somehow get on Voyager, it would take you roughly 20,000 years to get there. The fastest object we've ever sent. If you were riding on a rocket, like the Saturn V example, taking astronauts to the moon, the fastest we've ever sent a human, it would take you 70 to 80,000 years to get there. So maybe that puts in, and then you talk about farther exoplanets, multiple times, much farther, much longer. So we've got to figure out interstellar travel if we're getting anywhere. So Proxima Centauri b is the exoplanet. This is an artistic rendering of what that might look like. This exoplanet is here. It goes inside the habitable zone and comes outside the habitable zone. And it orbits a red dwarf star. This star and the next one, and I may not get to all these systems actually because I may skip some, but basically there are several systems that have been discovered with rocky planets like this one, so we call them Earth-like, that have surfaces that could be terrestrial, that could have water on the surface. They're in their habitable zones, which we can map, just like we know in our solar system. But this star, what's really cool is this star will last trillions of years. This is called a red dwarf. And the TRAPPIST system with 7 exoplanets is also around a red dwarf. There are many stars like this in the galaxy, and they'll last trillions of years. And I think I'm probably right. I'll only do a couple of these, but we don't have images of these exoplanets yet. So we have artistic renderings. If it's around a multiple system, maybe it'll look something like this on the surface, and here's some rocks and some clouds, but we don't know much beyond that. So anytime you see something like this, know it's a rendering, look at the fine print, and it'll say that because we have no images of this. This is TRAPPIST-1e. This is a system with 7 exoplanets. Maybe I'll just quickly go there. And by the way, if you're around a red dwarf, and the same thing with the TRAPPIST system here, which is actually 40 light years from Earth, is you got to snuggle up to that star to be habitable because the star is much smaller and dimmer. And because of that, there are flares that come out. You're closer to these solar storms and flares around these stars. And so therefore, it's not known yet how habitable this zone really is. And so that's something else that scientists are working out. So this is a 7-planet system, 7 rocky planets, 4 of which are in the habitable zone. And this is TRAPPIST-1e. There's another image, again, just a rendering, maybe something like this, who knows? Lots of nearby neighbors that you could see in the sky. But again, we can't get there yet. And JWST will be looking at this system, one of the first things that it does. And what I'm going to say, I'll just say that there are several systems where you have Earth's cousins, Earth-like planets around the same size of Earth in the habitable zone. These are all really interesting, and hopefully we'll get better data on them, knowing if they're habitable. Can we get there? Absolutely not. It could take millions of years to get to some of these, given the technology we have. So we really have to develop new technologies and develop the ones we have too, like nuclear maybe, to get to the stars. I think the last one I'm going to go to is 50, because I'm not going to have time, is 55 Cancri. And I like this exoplanet system because it's so bizarre. This one is, again, 40 light years away in another direction. And this one is a super Earth. There are actually several planets in this system. And here we go. You can go to all of these with OpenSpace, which is really awesome. It's fun to go around. Okay, so here we have a habitable zone. It's kind of an interesting example here. And again, with Kepler, with the Kepler mission and other telescopes, we're discovering all these really cool systems that are very unlike our solar system. And what does that mean? How unusual are we? Could there be life on these planets? It's hard to know. But if there's intelligent life, they're probably much more advanced than us, given our age of only 4.5 billion years. And they're several billion years older, several of these systems. We don't see evidence for them. So it's unlikely that it's near us if it's intelligent, but we don't really know. Okay, so there's several planets here. One goes in and out of the habitable zone. This is the last one I'll show you. I like this one because it is 55 Cancri E. It is not even close to the habitable zone. It's really up against this planet, but the way they know enough about this planet that, I'm going to skip this one, that it would be molten. It's a rocky planet, so it would be a complete lava world. And what scientists have been able to determine is that if it is a lava world, if they think what they think is right, the skies would sparkle because all the silicates in the sky would be reflecting the lava. And so the skies would be all sparkly, like a diamond sky, it would be a really sparkly sky. And what NASA does to just inspire kind of imagination is that maybe in the future, this is they make these travel posters for these exoplanet systems, is that this is an astronaut going to 55 Cancri E, lava life, skies sparkle above a never-ending ocean of lava. So maybe one day, if we ever get off this planet and figure out interstellar travel, we could have a vacation there. I'm sure some people would want to go to this lava planet, which is pretty spectacular. So anyway, that is all I'll say about my talk and habitability, and I hope you enjoyed it. So thank you, and I will take questions. Thank you, Chris.
Thank you, Rachel. Everybody, wherever you're at, give Dr. Smith a great big round of applause.
Oh, thank you. I hear
this on such a cool journey.
Thank you.
So we've got a couple of minutes for questions.
All right.
And then I'm going to log us out so that everybody can get to the next programs.
All right.
But we had lots of questions coming in about some of these different planets. First one, so could Venus be a future Earth?
Yeah, it seems hard. We don't know that answer, but it seems like that's a hard job. It would be easier to conceptually to terraform Mars than to figure out a way to get rid of Venus's atmosphere, because Venus has this thick atmosphere, and how are we going to get rid of that atmosphere? We don't know. We can't do it. We can't even control our own atmosphere, and Venus is 90 times, 100 times worse than that. So we're at stages not just before, but we're at a stage before that's amazing, runaway greenhouse, and we can't control that now. So it seems pretty unlikely we're going to figure out how to control Venus. And I would say if we're going to go to any planet, it would more likely be Mars than Venus, because we can't even get to the surface of Venus very easily. So I would say Venus, probably off the table. Maybe not Mars.
Yeah, that was also, that led into the next question that I had here, which is we're talking about sending humans to Mars pretty soon, but is it even possible to send humans to Venus?
No. Well, you could send them, but they won't come back. I mean, sure. You can't get to the surface. We can land on Mars and stay there with robots. We can see that. We're doing it. We're not going to be crushed and melted and boiled. You will be on Venus. And so Venus is a crushing atmosphere. It is extremely hot. Even robotic probes don't last more than a few hours. So certainly we can launch something to the planet. We've done that, but you can't send humans safely there at all.
And then looking at our time, the last question I'm going to take from YouTube. As the sun goes through its life cycles, or as any star does, what happens to the habitable zones?
Oh, that's a great question. So it depends on the star. So our sun is going to swell up like a red giant, is going to swell up to a red giant, and then the habitable zone will be pushed way, way out. And so that actually probably happened to Venus too. The star brightened, our early sun brightened and pushed that habitable zone out and cooked Venus. Eventually, our sun will engulf the terrestrial planets, and the habitable zone will be way out past maybe around the outer planets, but those planets aren't habitable anyway. So as a star dies, and certainly if a star is massive enough, it's supernovas, it pushes out that habitable zone. So the more massive the star, the farther away the habitable zone, and the less massive star, the more close that habitable zone. But as the star evolves, it'll either swell up, sometimes they shrink, afterwards it shrinks down, but then the system's not habitable anymore anyway. So it really depends on the type of star. But basically it pushes out as the star ages. Any other last questions?
Thank you very much.
Oh, okay.
Thanks, Rachel.
You're welcome. You're welcome. Thank you, everyone.
So everybody, we're going to drop a link to a survey.
Oh, yes,
that's
please.
Part of the OpenSpace project. Our moderator is going to take care of doing that. Please go and check out, fill out the survey, give us your feedback. All that stuff helps us. And we've got another Astronomy Days program coming up for you in just a few minutes. So we're going to jump off of this Zoom call. That way you can all head to the next program, Space as a Time Machine. Or if you're watching on YouTube, just head to back to our YouTube channel and you'll see the live video pop up there. Rachel, thank you so much.
Thank you, everyone. Thanks, Chris, and everyone. Have a great day. Space. Enjoy.
Happy Astronomy Days.
Bye. Bye.